Let's compute the expected value in the variance of gamma distribution with parameters alpha and beta. So we have some random variable xi with gamma distribution and parameters alpha and beta. Here we have the PDF of xi, which is given by x to the alpha minus 1, beta to the alpha, e to the minus beta x, divided by the gamma function in alpha, and multiplied by the indicator that x is at least 0. So we have that the PDF will be equal to 0 if x is less than 0. And here we have the gamma function of alpha, so the definition of the gamma function, which is the integral from 0 to plus infinity of t to the alpha minus 1 e to the minus t dt. Okay, but we also know that this holds for any alpha being a non-negative real number. But in one special case that we have, if alpha is a non-negative integer, then we have that the gamma function of alpha is just alpha minus 1 factorial. Okay, so now we can compute the expected value of xi. How do we compute that? Well, we have that xi is an absolutely continuous random variable. It means that we have to use the formula that we know for absolutely continuous random variables. We have that the expected value of xi is given by the integral from minus infinity to plus infinity of x multiplied by the PDF of xi. So let me write here the PDF of xi in x dx. So all that I have to do right now is just to replace the value of the PDF, so by this function right here, and then to compute the integral. Okay, so we have the integral from minus infinity to plus infinity of x, and this is the PDF that we have. So x to the alpha minus 1 times beta to the alpha times e to the minus beta x divided by the gamma function of alpha. And we have the indicator, and x is at least 0 dx. So the first thing that we have to notice is that we have this indicator right here. The indicator is going to change the limits that I have for my integral. So we can see that the function is going to be equal to 0 if x is equal to 0. So we have that the integral itself is going to be equal to 0 if x is less or equal than 0. So I can change this integral not from minus infinity. So I can't understand that the integral from minus infinity to 0 is going to be equal to 0. So I can write this in the following way. I will have that this is the integral not from minus infinity to plus infinity, but from 0 to plus infinity. Because again, the integral from minus infinity to 0 of this function, it will be just 0 because the function itself is equal to 0. And then I just write x. So what do I have? I have x to the power alpha, right? But I also have b to the power alpha. So let me write just x beta to the power alpha. So these together to the power alpha. And then I have beta, e to the power beta minus x, e to the power minus beta x. And I have to divide everything by the gamma function of alpha and dx. So I don't have to write the indicator function anymore because I already have included the indicator function right here. Okay. Now the next step is going to be the following. Let me multiply by beta and let me divide by beta. Okay. I will have the following. Then I will have this. So this is going to be equal to. I'm going to first this constant right here. So the gamma function of alpha, since alpha is given, this is a constant. Then the gamma function of alpha is a constant, is a number. So I will have that this is 1 divided by the gamma function of alpha. Okay. And I want to divide by beta. So this is the beta that I will have right here. And then I will have the integral from 0 to plus infinity. And let me see what I have. X beta to the power alpha, e to the power minus x beta. And then since I'm multiplying by beta, then I will have d of beta x. D of beta x, right? Now, what can I do with this? Well, we can notice that this is exactly the same that we had for the definition of the gamma function. This is exactly the same that we had for the definition of the gamma function. The difference is that instead of x beta, we have t, but that's okay because here we have dbx, right? So it doesn't matter. But the other difference is that here we have alpha. Here we have alpha minus 1. So we can write the following. we can change this alpha to make it alpha minus 1, sorry, alpha plus 1 minus 1, like this. Yes, so alpha is equal to alpha plus 1 minus 1. So the new alpha in this case is going to be alpha plus 1. So we get that actually this integral, all of this integral, is just equal to the gamma function of alpha plus 1. And then I can replace this and we have the following. So we'll have the gamma function of alpha plus 1 divided by beta by the gamma function of alpha. And now I have to use the properties of the gamma function. The property from the gamma function that I need is the following. I need that the gamma function of alpha plus 1, this is equal to alpha times the gamma function of alpha. So this property is very clear if we think about the second definition that we had for the gamma function. So here, if we look at this, then we can see that the gamma function of alpha plus 1 is actually alpha factorial, right? And here we have alpha multiplied by the gamma function of alpha. The gamma function of alpha is going to be alpha minus 1 factorial. So we have alpha multiplied by alpha minus 1 factorial, which is alpha factorial. So everything holds. And then we can replace this. And by the way, it's very important to notice that this holds not only for integers. This holds for any non-negative real numbers, okay? It's just that in the case of integers, the reason why this holds is very clear. Then I replace this by this, and we obtain the following. This is alpha times the gamma function of alpha divided by beta times the gamma function of alpha. Now I can cancel this gamma function of alpha, and I obtain alpha divided by beta, and this is the expected value of gamma distribution with parameters alpha and beta. Let's compute now the variance. So for computing the variance, we just need the formula that we know for the variance. We know that variance of any random variable xi, so the variance of any random variable xi, is equal to the second moment of xi, so the expected value of xi squared, minus the expected value of xi, and the whole thing is squared, right? So from here, we already know the expected value of xi. We already know that this is equal to alpha divided by beta. All that we have to do is to find the second moment, so the expected value of xi squared. So let's do that over here, okay? So right here, expected value of xi squared. So to compute this, the formula is very similar to the one we had for the expected value, this one. But in this case, we have xi squared. So we don't have the expected value of the random variable xi. We do have the expected value of a function of the random variable xi equal to xi squared. So instead of x right here, we will have x squared. That's the only difference that we'll have, okay? So let me write it. So here we'll have the integral from minus infinity to plus infinity of x squared times the PDF of xi, all right? Not the PDF of xi squared, but the PDF of xi in x. And then I can already skip this part right here. So we have the indicator. So actually the integral is going to be from 0 to plus infinity. And then we'll have the following. So here we'll have the integral from 0 to plus infinity of, we have x squared times beta to the alpha. So, no way, we actually have x squared times x to the alpha minus 1. This is equal to x to the alpha plus 1. X to the alpha plus 1. And then we have beta to the alpha, right? Beta to the alpha. But I do want again somehow to use the same trick that I used before so that I make this the gamma function. If I want to do that, then I need x and beta to have the same number, the same expression in to the power, yes? So we need here alpha plus 1. Then since I write plus 1, then I need to write minus 1. So in other words, I'm multiplying by beta and I'm dividing by beta, yes? And then we still have e to the minus beta x divided by the gamma function of alpha and dx. So let me compute that right here. Let's see what we obtain. So first of all, let's take this constant out. So here we have the gamma function of alpha. So we'll have 1 divided by the gamma function of alpha. Next, we have to divide by beta, so that here we just keep alpha plus 1. But we also need here d of beta x. So we need to multiply by beta and we need to divide by beta again. So we actually have to divide twice by beta. So we'll have that this is beta squared right here. Yes. And finally, we obtain that this is here the integral from 0 to plus infinity of x times beta to the power alpha plus 1 times e to the minus beta x d of beta x. And with exactly the same logic that we had before right here, this is going to be just the gamma function of alpha plus 1. This is equal to the gamma function of alpha plus 2 we will have right here. Because here, if we need minus 1, then alpha plus 1 is equal to alpha plus 2 minus 1. So this is alpha plus 2 over here. Then finally, this is equal to the following. The gamma function of alpha plus 2 divided by the gamma function of alpha times beta squared. So by the property that we had right here, this one from here, we obtain that the gamma function of alpha plus 2 is just alpha plus 1 times the gamma function of alpha. So alpha plus 1 times the gamma function of alpha divided by the gamma function of alpha times beta squared. So we can cancel the gamma function of alpha here, and we obtain finally that the second moment is given by alpha squared divided by beta squared plus alpha divided by beta squared. So this is the answer for the second moment of psi. And now we can use this to compute the variance. So here we have the variance. Now all that I have to do is to replace the values that we already found. So we have that this is the second moment right here. Alpha squared divided by beta squared minus alpha divided by beta squared minus the expected value of psi squared. So we already have that the expected value of psi is equal to alpha divided by beta and the whole thing is squared. So we can easily see that we can cancel this with this. And here we don't have minus, here we have plus. So the answer will be alpha divided by beta squared. So we have proven that the expected value of psi will be equal to alpha divided by beta, and the variance of psi will be equal to alpha divided by beta squared.